We're going to continue discussing the solutions of a differential equation without necessarily solving the differential equation. In particular, we're going to talk about solution curves today, which will take us through direction fields and also talk about the trajectory of the solution of a differential equation. Okay, so let us consider the differential equation dy dx is equal to a function of x and y. Okay. So this means that we end up with a solution that is in the form y is equal to another function, maybe phi of x. Okay. And if we draw the solution, if we plot this solution on the xy axis, say this is your x-axis and that's your y-axis, you might end up, let's say we get something of this form, something like this, all right? Then we can see that, let me make it a little bit more, how do I want it? Okay, same thing, but I think I know what I want. All right, so this is y equals phi of x, okay? If you look at this, at each point, you can figure out what the slope of the tangent line is if you draw the tangent line or draw a point, and then say you draw a line that is tangent to the curve at that point. So in this case, this is a tangent line, and then maybe another one over here, which I'll zoom in so we can get another tangent line over here. So each of this, the slope of this, right, the slope of this tangent line is would be the derivative dy dx, okay, at that point, at whatever point we are here, okay? So what is this telling us? This is telling us that we can actually draw the slope, draw these tangent lines by just looking at the differential equation, because the tangent line is the derivative dy dx. And for this differential equation, we're just given the first derivative, okay? So these tangent lines are called, I forgot their name. They're called lineal, yeah, lineal, like this, all right? So this would be, if this point is, say this is point, let's call this point, this A and this B. So this is AB, all right? So this would be the lineal. Oh no, why did I do that? Okay, so this particular lineal will be the lineal element at the point AB, okay? All right, so that's what I want to say about that. Let me move this over here and make it a little bigger. Move this over here and then zoom in into this just a little bit. Okay. So with this, we can draw a bunch of the lineal. And if we draw a bunch of them, that is called, collection of them is called a direction field. Let's give it a formal definition, right? A direction field, or it's also called a slope field. A slope field is a collection of linear elements. that can be used to trace solution curves of a given ODE, given ordinary differential equation. Okay, so what I'm saying is that if you have a bunch of these lineals, so for instance, if at any given point you're able to use the differential equation to create a lineal, so for instance, if you have all these lineals here and you know in what direction they're going, you can always use it to trace the direction or to trace a curve. If, for instance, if you're told that a differential equation, that the initial condition is this point, right? Then you can actually use these lineals to trace the solution curve of the differential equation. All right, so let's do an example, and this example will involve sketching lineals by hand, but in real world, in practice, it's very difficult to sketch by hand, but I'm just gonna sketch a few of them, and then I will tell you what the slope field looks like. And then in class, if you are taking this course in class, then we might be able to try doing them using either MATLAB, Maple, or Python. I know how to do it in MATLAB, and I think I can remember how to do it in Maple. I haven't tried it in Python, but I'm really excited to try it and see and let you guys know what it looks like. Okay, so sketch a direction field for the differential equation 0.5 xy dy dx is equal to 0.5 xy in the region. Let's do the region -0, no, -4. X is between -4 and 4, and also y is also between -4 and 4. Okay, so I'm going to start by drawing my region. This is an iPad. Maybe I should do -2 to 2. What do you guys think? You watching? Let's do -2 to 2. That might be more merciful to me. And then I'll just erase everything. -2, 2. All right, so I'm gonna go, this is my y-axis, and that is my x-axis. Okay, I'm gonna extend this here. So this is -1, this is -2, this is 1, and that is 2. This is -1, and that's -2. All right, so I'm gonna pick a bunch of points. Or let me focus. This is 1. Why am I not drawing this to scale? It's fine though. This is 1, and that is 2. Okay. No, I want to do this. I'm just going to pick a bunch of points around where y is 1. So we can do it where y is 1, where y is 0, where y is 2, and so forth. So let me focus on when y is 1. At y, I'm going to do at y equals 1. Then I'm going to create a table. Stay with me. I'm going to create a table. A table for the values of what's x and then what's dy dx. Okay, so dy dx, we know that dy dx is 0.5 xy. Okay, so when x is, oh, why am I move this over here? All right. Let's do this. Let's get this down here over this place. Okay. And I'm going to bring my x here. Okay. So I'm just focused with when x is equal to 1. When x is equal to 1, let's start with y being negative 2, negative, negative 2, negative 1, 0, 1, and 2. All right. And then we're dealing with 0, 0.5, 0.5 xy, which in this case is our dy dx. Okay. So when y is 1 and x is negative 2, 0.5 times dy dx is negative 1, right? And this would be negative 0.5, and this would be 0, this would be 1, this would be, no, this would be 0.5, this would be 1, okay? All right, so I just got my values for when x is equal to 1, when y is equal to 1. So in practice, we would do it for when y is equal to a lot of values, when y is equal to every value between negative 2 and 2, okay? But I'm only going to do one here for the sake of time, and then I'll tell you what the others look like. So let's start with negative 2. This is when this is negative 2, negative 1, 1, 2. All right. When y is 1, this is where y is 1, and x is negative 2, we have a slope of negative 1. A slope of negative 1, I'll estimate it. I'll say it looks like that. And then when x is negative 1 and y is 1, a slope of 0.5, negative 0.5, not 0.5, negative 0.5 would look something like this, right? And then when x is 1 and y is 1, a slope of 0 would be that. And then we get a slope of 0.5. And then we get a slope of 1, like this. I guess I don't want it to be the same as that of 0.5. All right, 0.5. I want something like this, and then I want something like that. Okay. So what do we have? We're going to end up having a bunch of slope fields that look like this, you know. So if you look at the equation, you will see that the slope fields, there will always be 0 along the axis, right? There will always be 0 no matter the value of y. And then it turns out that this will become flatter as we get towards the origin, or towards the x-axis, and then they will start increasing again in their slope, but in this case they will become more negative. So here it should start increasing and increasing and so forth. Same thing with this, the points over here and so forth. All right, so that's what you get if you take your time and do this for a lot of values of y. So you might want to try for when y is equal to, let's say, start with when y is negative 1 and do all this, or negative 2, when y is negative 1, when y is 0, when y is 1. We did for when y is 1, and then when y is 2. For each of these values of y, you do your table and you draw these little lineals. And after drawing them, you get a field like this. So with this field, you can now trace, it now gives you the direction of your curves. So if you start a curve somewhere here and you want to get the curve, the solution curve, so this would be a solution curve, for instance. Another solution curve would be something like this. and it will go like that. All right. Okay, so that's the thing with lineals and solution curves and direction fields. All right, so let's look at another definition. Another definition. We're going to talk about an autonomous ODE. An autonomous ODE is an ODE that the right hand side does not depend, does not that the right hand side doesn't have any independent variable, right? In other words, we can write the differential equation without any of the independent variable. So I'm going to write it. A differential equation, an ODE, is said to be autonomous. It's said to be autonomous if the independent variable does not appear explicitly in the equation. So for instance, if it's a dy dx, then it's just going to be dy dx is a function of y, not a function of x and y. So this would be a first order ODE that is autonomous. So maybe other concrete examples would be something like y prime is equal to 2y, you know, or like y prime is equal to natural log of y plus cosine of y, stuff like that. Or dy dx is equal to 2 minus y all times y, stuff like that. All right. Now, the last thing I want to talk about is what we call a critical point, and then I'm going to give you an example on that. Like definition. In differential equations, a critical point is the point where f of c is a point c where f of c is equal to 0. Right? And when I say f, I just mean the right-hand side of the equation. All right? So a real number c is called the critical point of the differential equation dy dx is equal to f of y. So this is autonomous. We're defining this just for autonomous. If f of c is equal to 0, right? So it's also called stationary points. A stationary point. It's also called equilibrium point. It's also called fixed point. Okay. All right. So let's do some examples. Okay. So let's look at the differential equation dy dx is equal to y times 2 minus y, right? So our critical points, the critical point here would be if we set y times 2 minus y equal to 0, set y minus 2 is equal to 0. This tells us our critical points are y equals 0 and y equals 2. These are our critical points. Okay? All right. Now, draw a phase portrait. Okay, we haven't talked about this, but I'll explain with this example. Draw a face portrait of the ODE. Okay, to draw the first face portrait, we're going to assume this is our f of y. This is our f of y. The first thing you want to do is to look at the demarcations of the demarcations that have been created by the critical points. What do I mean? So let's see. We have our critical point is 0 and 2. So if I think of, so that means from negative infinity to 0 might have one behavior, and then 0 to 2 might have another behavior, and then 2 to infinity would have another behavior. And stay with me, I'm going to explain what I mean by behavior. Okay? So if that's the case, in this interval, what is the sign? What's the sign of f of y? What's the sign of f of y? Is it positive? Is it negative? All right? And then, how does y of x behave? Okay. So let's look at our equation. Our equation is y dy dx is equal to y times 2 minus y. Okay. So if you plug in, pick a number that's negative. If you pick a negative number and you plug it into a negative number that is that is less than 0. So let's pick negative 1. If we plug negative 1 in for y, this part is going to give us positive, but this will give us negative. So this is negative. The sign is negative. If you pick a positive number between 0 and 2, let's say we pick 1, we get positive here. And this will give us negative. You see where I'm going with this? All right. Then, so if that is the case, since y of x, f of y is a derivative. Remember, this is our f of y. So f of y is a derivative of y of x. So if you have f of y negative, that means y of x is decreasing here. Y of x is increasing, and y of x is decreasing here. Okay. So with this table, we can now fully describe the behavior of our fixed points, or our equilibrium points. All right, so this, what I'm going to draw here is very important. So I'm going to assume this is my x-axis, or my y-axis, actually. Let's see. Oh, no, I didn't want that. Come on. All right, so this is my y-axis. All right? On my y-axis, I have two fixed points. One is at 0. The other is at 2. Okay. Maybe not to scale, but you know what I mean. You know why I just want to illustrate something. So this is y equals 0. Y equals 0. Y equals 2. Okay. When y is when y is between negative infinity and 0, y is decreasing. So what do we have? We have this trajectory that's decreasing here, right? When y is between 0 and 2, y is increasing. When y is 2 to infinity, it's decreasing. When we start at, when I say is, I mean when we start at y below 0, it's going to just go away from 0. And when we're in this point and we start anywhere here, we're going to go towards 2. So you see that whenever you are at 2, or whenever you're approaching 2, either from the top or from the bottom, it's going to tend towards 2. So this is called an attractor. 2 will be an attractor, or it's a stable equilibrium point or stable equilibrium solution. We're going to use solution. Okay. How about y equals 0? This is a repeller. And this would be an unstable equilibrium solution. Okay? All right. And I'm going to do something here. I'm going to paint this, instead of blue, I'm going to, I'm going to make a hole, make it have a hole. All right? And at a point in time, I'll explain why. And, well, I can explain now. Why am I hiding it? This is because my stuff is not writing anymore. What is going on? Oof. No, come on. Okay, I got it. Okay. This is because attractors, by convention, they are field circles, and repellers are not field circles. So that's just by convention. It's just a way to denote that, oh, this point is an attractor, this is a repeller. Okay, so another solution, or another problem. Let's draw a typical solution to, in each region. When I say each region, I just mean each region determined by the critical point. I don't want to spend time writing that. Okay, so you remember this. I'm gonna cut this, or copy it. I'm gonna put it here. So we have this. We can now say, so if we start at 2, since 2 is an equilibrium point, if our initial condition is that y is 2, x is something, but y is 2, then it's gonna stay at 2. So let's draw a line there, this line, okay? 0, the same thing. Now, what do we know? We know that 0 is a repeller and 2 is an attractor. So if you now start at any point, if you want to find a solution of this equation, and you start at a point where y is equal to 2, right? The trajectory is going to move towards y. If you start at a point between 0 and 2, the trajectory is going to move towards y equals 2, because it's an attractor, and you see where the arrow is going. If you start anywhere here, the trajectory is going to go there, and it's not going to ever cross 2. So it just means that it's tend towards the equilibrium solution, which is y equals 2. So if you start over here, since y equals 0 is a repeller, it's just going to diverge. It's never going to go towards y equals 0. Okay. All right. So we're going to stop here. I'm going to stop here, and I will explain more about this in class if you're taking the course, or we'll also do more examples. Oh wow, I want you to try one. Let me give you one to try. How about try this? Do Find a critical point, draw the face portrait, and draw a typical solution region. For these examples, try number 2, try um, dy dx is equal to y squared, 4 minus y squared. And then number 3, dy dx is equal to 10 minus 3y minus y squared. Okay, so I want you to try this yourself. Okay. All right. So before I go, I know I'm supposed to have gone. Before I go, I just want to note. I just want us to note something. The solution curves. The solution curve. Do not. So these are the I call them trajectory. They're also the solution curves. The solution curves do not cross the equilibrium solution. So what I'm calling equilibrium solution is wherever, when we get the equilibrium point, the solution y equals 2 will be an equilibrium solution. So this is an equilibrium solution. Even though this is a stable equilibrium solution. Stable equilibrium solution. And this is an unstable equilibrium solution. All right, so I want you to try this. So that's the first thing I want you to note. The second thing I want you to note that a solution we're gonna talk more about this, right? Okay, I'll see you in the next video.